Welcome back. Here is the question that organizes this whole episode. You have a subspace, a line, a plane, the column space of a matrix, and you have a vector that does not lie inside it. Among all the vectors that do lie inside the subspace, which one is closest to your vector? That closest vector is called the orthogonal projection, and you can picture it as the shadow your vector casts when light shines straight down onto the subspace. We'll build it in stages. First, we define orthogonal and orthonormal vectors, and the orthogonal complement of a subspace. Then, we project onto a single line. Then onto a whole subspace, which we'll describe as the column space of a matrix A. That gives us a single matrix, the projection matrix, that does the projecting for us. We'll prove its two signature properties and see why the leftover error always points perpendicular to the subspace. Let's begin. Start with the two words in the title. Two vectors are orthogonal, just a fancy word for perpendicular when their dot product is 0. That's the whole test. Multiply corresponding components, add them up, and if you get 0, the vectors meet at a right angle. A set of vectors is orthonormal when two conditions hold together. First, the vectors are mutually orthogonal. Every pair has dot product 0. Second, each vector has length exactly 1. That's the normal part, short for normalized. So orthonormal means perpendicular and unit length all at once. Why do we care so much? Because orthonormal bases make coordinates trivial. If you have an orthonormal basis and you want to know how much of a vector points along each basis direction, you don't solve any equations, you just take dot products. The amount of v along q1 is simply v dotted with q1. That single fact is why the rest of this section keeps chasing orthonormal bases. Now, a subspace, not just a single vector. Given a subspace S sitting inside Rn, its orthogonal complement, written S with a little perpendicular symbol, is the set of all vectors that are perpendicular to every single vector in S, not just one of them, all of them at once. This complement is itself a subspace, and it interlocks with S beautifully. The only vector they share is the 0 vector. Their dimensions add up to n, the dimension of the whole space. And most important for us, every vector v in the whole space splits in exactly one way into a piece living in S plus a piece living in the complement. That unique split is precisely what projection computes. The piece in S is the projection. There's a fundamental example worth remembering. For any matrix A, the orthogonal complement of the column space is the null space of A transpose, the left null space. The two subspaces we met earlier in the course turn out to be perpendicular partners. Let's do the simplest case completely, projecting a vector b onto a line, the line spanned by a single vector A. The projection must lie on that line, so it's some scalar multiple of A, call the scalar x hat. Now here is the idea that powers everything, choose x hat so that the error, b minus the projection, is perpendicular to A. Set the dot product of A with that error to 0, expand it, and out drops x hat equals a dot b over a dot a. So the projection of b onto the line is a dot b over a dot a times A. Now watch a small piece of algebra that pays off hugely. We can rewrite that as the matrix A times A transpose divided by A transpose A, all multiplying B. The bottom, A transpose A, is just a number. The top, A times A transpose, is a full square matrix. So projection onto a line is multiplication by a fixed matrix P. Hold that thought, we're about to do the same thing for an entire subspace. Now the real prize, project B onto a whole subspace, the column space of a matrix A. The projection lies in that column space, so it's a combination of the columns, that is, A times some coefficient vector x hat. Same idea as before, just more of it, the error, b minus ax hat, must be perpendicular to every column of A. Stacking all those perpendicularity conditions into one statement, A transpose times the error equals the 0 vector. Multiply that out and rearrange, and you get the single most important equation in applied linear algebra. A transpose A times x hat equals A transpose B. These are called the normal equations, normal, again meaning perpendicular. If the columns of A are independent, the matrix A transpose A is invertible, so we can solve x hat equals the inverse of A transpose A times A transpose B. Multiply by A to get the projection itself, A times the inverse of A transpose A times A transpose times B. There's our projection matrix sitting between B and the answer. Let's name and study that matrix. P equals A times the inverse of A transpose A times A transpose. Feed it any vector B and out comes PB, the projection of B onto the column space of A. Two properties pin this matrix down completely. First, it is idempotent, P squared equals P. In words, once you've projected a vector into the subspace, projecting again does nothing because it's already there. The shadow of a shadow is the shadow. Let me show the algebra. P squared is A times the inverse of A transpose A times A, And here the middle piece, A transpose A times its own inverse, collapses to the identity, leaving exactly P again. Second property, P is symmetric, P transpose equals P. Together, idempotent and symmetric, these two properties actually characterize orthogonal projection matrices completely. One bonus, the matrix I minus P, is also a projection. It projects onto the orthogonal complement, and it produces the error vector directly. The projection and the error are computed by complementary matrices that add up to the identity. Before the figures, one special case that pays off enormously. Suppose the columns we're projecting onto are already orthonormal, perpendicular, and unit length. Call that matrix Q. Then Q transpose Q is just the identity, and the projection matrix P equals Q times the inverse of Q transpose Q times Q transpose collapses to simply Q times Q transpose. The inverse vanishes because there's nothing to invert. Even better, the projection of B becomes a plain sum, add up for each orthonormal direction, the dot product of B with that direction, times the direction. Each term is just the projection onto a single axis, and you total them. Compare that to the general case, where we had to invert A transpose A, a real computation. With an orthonormal basis, the whole thing dissolves into dot products. That spectacular simplification is exactly why, next episode, we go to the trouble of manufacturing orthonormal bases on demand with Gram-Schmidt. Let me justify the word we keep using, closest. The claim is that the projection PB really is the unique closest point of the subspace to B. No other point in the subspace is nearer. Here's the elegant one-line proof, and it's just Pythagoras. Take any other point S in the subspace. Split the distance from B to S into two legs, from B to the projection P, and from P to S. The first leg is the error, which is perpendicular to the whole subspace. The second leg, P minus S, lies inside the subspace. So the two legs are perpendicular to each other, and Pythagoras says the squared distance from B to S equals the squared distance from B to P, plus the squared distance from P to S. That sum is smallest exactly when the second term is 0, which means S equals P. So the projection wins always. The perpendicular drop is the shortest one, and that single fact is the entire geometric reason least squares works, which is where we're headed in 2 episodes. Here is the whole episode in one picture. The light blue tilted plane is our subspace S. Think of it as the column space of A, and it passes through the origin. The bold navy vector B rises up out of the plane. It does not lie in S. To project it, we drop straight down from the tip of B until we hit the plane. The green vector lying flat in the plane, from the origin to that landing point, is the projection, PB. And the gold dashed segment connecting the tip of B down to its shadow is the error vector, B minus PB. Look at the little red square where the dashed line meets the plane. The error is perpendicular to the plane, perpendicular to every vector in S. That right angle is not decoration. It is the entire definition. The projection is the one point in the plane for which the leftover error stands exactly perpendicular. Everything else, all the algebra with normal equations, is just this right angle written in symbols. This second figure strips the idea down to its skeleton. The horizontal line is the subspace S, and the vertical line through the origin is its orthogonal complement, every vector perpendicular to S. They meet at a right angle, as complements must. Now the navy diagonal arrow is our vector B. Watch it split. Drop a green arrow along S, that's the projection, the part of B that lives in the subspace. Then an orange arrow straight up along the complement, that's the error, the part of B that no element of S can reach. The two pieces meet at a right angle, and together they reconstruct B as their diagonal. This is the unique orthogonal decomposition. B equals the part in S plus the part in the complement. Projection is nothing more than keeping the first piece and discarding the second. When we say PB is the closest point in S to B, this right angle picture is the reason. The perpendicular drop is always the shortest one. Let's compute one. Project the vector 1, 1, 1 onto the line through the vector 1, 2, 2. Two dot products do the whole job. First, a dot B, 1 times 1, plus 2 times 1, plus 2 times 1, gives 5. Second, a dot A, 1 plus 4 plus 4, which is 9. The projection is a dot B over a dot A times A, that's 5/9 times the vector 1, 2, 2, giving the vector 5/9, 10/9, 10/9. Now the habit you should never skip, check that the error is perpendicular. Subtract the projection from B to get the error vector 4/9, -1/9, -1/9. Dot it with A, 4/9 minus 2/9 minus 2/9, which is 0. Perfect. The error came out perpendicular to A exactly as the construction demanded. If that dot product had not been 0, we'd know we made an arithmetic slip. The orthogonality check is free insurance on every projection. Now let's build a full projection matrix and watch it work. Take A to be the 3×2 matrix whose two columns are 1, 0, 0, and 0, 1, 0. These span the xy plane sitting inside three-dimensional space. Follow the formula. First compute A-transpose-A. Because the two columns are already orthonormal, A-transpose-A comes out as the 2x2 identity matrix, and its inverse is again the identity. So the projection matrix P is just A times A transpose. Multiply those out, and you get the 3x3 matrix with 1s in the first two diagonal slots and a 0 in the third. Let's test it on the vector 4, 5, 6. Multiplying gives 4, 5, 0. It kept the x and y components untouched and crushed the z component to 0, which is exactly what projecting onto the xy plane should do. And you can check p squared equals p, squaring that diagonal matrix leaves it unchanged. The formula delivered the projection we already understood geometrically. One more, the general case, so you see the normal equations earn their keep. Project the vector 6, 0, 0 onto the column space of a 3x2 matrix, A whose columns are 1, 1, 1, and 1, and 1, 0, negative 1. Compute the two pieces of the normal equations. A transpose A comes out as a tidy 2x2, 3 and 2 on the diagonal, zeros off it because the two columns happen to be orthogonal. A transpose B comes out as 6, 6. Now solve A transpose A times x hat equals A transpose B. Since A transpose A is diagonal, we just divide 6 over 3 is 2, 6 over 2 is 3. So x hat is 2, 3. The projection is A times x hat, 2 times the first column plus 3 times the second, which gives the vector 5, 2, negative 1. Finally, the error, B minus P, is 1, negative 2, 1. Check it against the columns. A transpose times the error is the 0 vector, so the error is perpendicular to both columns. The projection landed in the column space and the error stands perpendicular, exactly as promised. A little history, because this idea has deep roots. Around 1800, Carl Friedrich Gauss and Adrien Marie Legendre independently developed least squares to fit astronomical data, and although they described it as minimizing the total squared error, what they were really doing, we now know, is orthogonal projection. In the late 19th and early 20th centuries, Jürgen Peterson Graham and Erhard Schmidt gave the systematic process for turning any basis into an orthonormal one, which is our very next episode. Then David Hilbert and Schmidt lifted projection into infinite dimensions, into what we now call Hilbert spaces, and there the projection of a function onto a set of orthonormal waves is exactly a Fourier series. Finally, in the 1930s, John von Neumann made projection operators the mathematical heart of quantum measurement. One humble condition, make the error perpendicular, runs through 3 centuries as mathematics and physics. Let's recap. Two vectors are orthogonal when their dot product is 0, and a set is orthonormal when the vectors are mutually orthogonal and each has length 1. The orthogonal complement of a subspace collects every vector perpendicular to it, and the dimensions of a subspace and its complement add up to the dimension of the whole space. To project onto a line through A, the projection is a dot B over a dot A times A. To project onto a subspace, the column space of A, we solve the normal equations. A transpose A times x hat equals A transpose B. Bundling that into one matrix gives the projection matrix P equals A times the inverse of A transpose A times A transpose. It is idempotent, P squared equals P, and symmetric, and the matrix I minus P projects onto the complement. The error, B minus PB, always lies in the orthogonal complement, perpendicular to the whole subspace. Next episode, we make all of this effortless by manufacturing orthonormal bases with the Gram-Schmidt process, and we package the result as the QR factorization. Today we learn to project. Two vectors are orthogonal when their dot product is 0, and a set is orthonormal when the vectors are mutually orthogonal and each has length 1. The orthogonal complement of a subspace is the set of all vectors perpendicular to every vector in it. To project a vector B onto a line through a vector A, we slide along A until the leftover is perpendicular, which gives the projection equal to a dot B over a dot A times A. To project onto a whole subspace spanned by the columns of a matrix A, we demand that the error be orthogonal to every column, and that single condition gives the normal equations, A transpose A times x hat equals A transpose B. Solving them, the projection of B onto the column space is A times the inverse of A transpose A times A transpose times B. The matrix sandwiched in the middle is the projection matrix P. It satisfies two defining properties, P squared equals P, because projecting twice changes nothing, and P is symmetric. The error vector, B minus PB, lies in the orthogonal complement of the column space. It is exactly the part of B that no combination of columns can ever reach. Next episode, we make projection effortless by building orthonormal bases with the Gram-Schmidt process and packaging the result as the QR factorization. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.